You open your eyes, and all around you is a pleasant landscape of rolling sand dunes leading to a quiet lake. The surface of this lake shakes slightly, breaking the reflection of the white clouds floating slowly overhead. On the other side of the lake, heavy rains carve the surroundings, and it looks like sunset's about to begin, because the whole sky is painted the color of a pumpkin. Welcome to the surface of Saturn's largest moon, Titan. It is the second largest satellite in the solar system, just after Ganymede, the satellite of Jupiter. With a diameter that puts it even ahead of Mercury and Pluto. The largest moon of Saturn, Titan, could contain life, scientists have discovered. With its significantly thick, nitrogen-rich atmosphere and saltwater oceans beneath a rigid ice sheet, Titan is the most Earth-like world we've ever found. Moreover, although Titan is a satellite of Saturn, it has all the attributes of a full-fledged planet. Clouds, rain, rivers, lakes, and even an underground saltwater ocean. The search for alien worlds suitable for life has long been a subject of interest to scientists. Although the planet Mars attracts more attention, it's turned out that within the solar system, there are worlds much more interesting in this respect than the Red Planet. The information available to scientists today, obtained from the Cassini space mission, shows the possibility of life actually existing on Titan. Although we have learned some amazing things about Titan, many questions remain about this satellite. Dear traveler, good morning. Today, we're going on a journey beyond the edge of the asteroid belt, towards the ring giant, to discover a world with incredible features. Before leaving for a new adventure, think of liking the video and subscribing to the channel to not miss anything. Thanks to all, and have a nice trip. Discovered by the Dutch astronomer Christian Huygens on March 25, 1655, and named after ancient deities of Greek mythology, Titan is Saturn's most interesting moon, and the second largest in our solar system, and the only one with a dense atmosphere. The true nature of Saturn's largest moon remained a mystery until the Cassini spacecraft visited the giant planet system, making 127 close flybys of Titan. Cassini also sent a small landing probe to Titan in 2005, Huygens from the European Space Agency. It is he who helped us to lift the veil of the secrets of the surface of Titan. The size of this moon allows it to compete with the planets of the solar system. This celestial body has a diameter of 5,151 kilometers. That's almost 3,200 miles in diameter, which is larger than the diameter of Mercury, slightly smaller than Mars, and it's almost 50% wider than the Moon. The mass of Titan is 1.345 times 10 to the 23rd kilograms, 45 times larger than the mass of our planet. By its mass, Saturn's satellite is the second largest in the solar system after Ganymede, the satellite of Jupiter. Despite its impressive size and weight, Titan has a low density, only 1.88 grams per centimeter cubed. For comparison, the density of Saturn is 687 kilograms per meter cubed. Scientists have identified a weak gravitational field in the satellite. The force of attraction on the surface of Titan is 7 times weaker than the Earth's parameters, and the gravity on the surface of the satellite is almost the same as on the Moon, at 1.35 against 1.62 on the Moon. A characteristic feature of Titan is its position in space. Saturn's largest satellite orbits its parent planet in an elliptical orbit at a speed of 5.5 kilometers per second, or 3 miles per second, outside the region of Saturn's rings. In addition, the average distance between Titan and the surface of Saturn is 1.22 million kilometers, or 621,000 miles. The entire system is 1.43 billion kilometers, or 621 million miles from the Sun, which is 9.5 times the distance between our central star and Earth. Therefore, it takes about 80 minutes for sunlight to reach Titan, so because of their great distance, the sunlight on this moon is about 100 times weaker than on Earth. Like our moon, Titan always faces Saturn from one side. Thus, Titan takes 15 Earth days and 22 Earth hours to complete an orbit around Saturn. The latter takes about 29 Earth years to orbit the Sun. Because Saturn and its satellites have a fairly high tilt angle of the rotation axis with respect to the ecliptic axis, there are seasons on the surface of Titan. Certainly, each of these seasons lasts more than 7 Earth years. Each of them on Titan follows the same calendar as Saturn. The seasons last more than 7 Earth years, but because of Saturn's orbital eccentricity, the northern summer and southern winter last longer than their opposites. A complete cycle takes 29 Earth years. In addition, every 7.5 Earth years on Saturn's satellite, summer is replaced by a cold winter period. According to astronomical observations, autumn is on the side of Titan that faces Saturn today. Nowadays, the satellite hides from the sun's rays behind the parent planet, which is why the Titanic autumn is replaced by a long and fierce winter. The temperatures on the surface of the satellite vary between -140 and -180 degrees Celsius, or -292 degrees Fahrenheit. The data obtained from the space probe Huygens revealed a curious fact. The difference between polar and equatorial temperatures is only 3 degrees, or a difference of 37 degrees Fahrenheit. This is explained by the presence of a dense atmosphere, which prevents the effects of the sun on the surface of Titan. In winter, the surface of the satellite is covered with snow from ethane, water vapor particles, and ammonia. As for the internal structure of Titan, as is the case for all telluric and rocky planets, scientists believe that Titan has a solid core, not formed of iron-nickel as on the first 4 planets of the solar system, but of rocks. This is only a small part of what we know about Titan. Many surprises are still to be discovered, whether it is around astronomy, climatology, glaciology, or microbiology, could be revealed in future space missions. Until the arrival of the international mission Cassini-Huygens on Saturn in 2004, its natural moons were a deep mystery. On January 14, 2005, this mystery slowly began to dissipate when the Huygens lander landed on the surface of Saturn's largest moon, Titan. For more than a decade, the Cassini spacecraft has shared the wonders of Saturn and its family of icy moons, taking us to incredible worlds. The mission of the automatic station Cassini has helped to lift the veil of fog that reigned over this star. For 4 years, the spacecraft orbited Saturn, taking sequential photographs of its satellites, including Titan. The research of the probe Cassini was carried out using a camera with an infrared filter and a special radar. The photographs were taken from different angles at a distance of 900 to 2,000 kilometers, or 1,200 miles from the surface of the satellite. After 7 years of flight through the expanses of the solar system, the station delivered the space probe Huygens to Titan. The lander penetrated the dense layers of Titan's atmosphere and descended by parachute for 2.5 hours. During this time, the probe's equipment studied the composition of the satellite's atmosphere and photographed its surface from a height of 150 kilometers, or 93 miles, 70 kilometers, 43 miles, 30 kilometers, 18 miles, 15 kilometers, or 9 miles, and 10 kilometers, or 6 miles. After a long descent, the spacecraft landed on Titan's surface on January 14, 2005, on a frozen surface. After landing on the Moon, Huygens operated for 72 minutes, transmitting to Earth via Cassini a lot of useful information directly from the surface of the satellite. Using images taken by the Cassini spacecraft and the Huygens probe, a team of researchers compiled a map of Titan. The results that the scientists obtained from the Cassini spacecraft and the Huygens probe have proven invaluable. Before these images, Titan appeared to everyone as a distant satellite where its surface was a huge expanse of ice, but the subsequent detailed study of its surface has changed the idea about Titan. In the images taken with the probe Huygens, it was possible to distinguish in detail the surface of Saturn's satellite, which was mainly made of solid water ice and sedimentary layers of organic nature. Moreover, it turned out that the dense and impenetrable atmosphere of this distant satellite has almost the same composition as that of the Earth. After 20 years in space, the spacecraft is running out of fuel. As NASA explained, in order to protect Saturn's moons, Cassini was sent to the Ring Giant, a final daring mission that sealed its fate. On September 15, 2017, the ship completed its mission and burned up in the atmosphere of the gas giant. In 2019, NASA chose the Dragonfly mission to explore this strange world in 2027. As the name implies, the mission will involve some sort of robotic helicopter that will fly across the surface of the satellite as a larger version of the Ingenuity drone that is currently exploring Mars with the Perseverance rover. The science team behind the Dragonfly mission has defined its goals and objectives. Its main task will be to study the chemical processes that take place on Titan, mainly those that could take place on Earth before the appearance of life. In addition, Dragonfly will look for biochemical signs that could indicate any type of past or present life. The features on Titan will allow Dragonfly to fly comfortably above the satellite's surface with minimal energy consumption. The dense but not too turbulent atmosphere and low gravity of the satellite will allow the Dragonfly probe to fly using a conventional multi-rotor pattern for short flights from one location to another and exploring different areas of the surface. The team has chosen a landing site that will give them access to places where the answers to all these questions lie. Initially, Dragonfly will land in 2034 at Shangri-La, a vast dune field near Titan's equator. It's a safe and interesting place for scientists to sample organic sediments, and then explore nearby areas for water ice samples. The probe will stay at each location for a full day on Titan, about 16 Earth days, before flying off and moving to a new location. It will eventually head to Celt Crater, a 90-kilometer wide crater, nearly 55 miles wide, that may show signs of water mixing with organic matter on the surface, where it will study older, deeper rocks for evidence of probiotic reactions. The planetary probe is expected to travel a total of about 160 kilometers, or 100 miles, during its 3-year mission. That's almost double the distance traveled by any rover that has ever existed. As a result, the images and data we will get could be some of the most breathtaking we've ever seen. After decades of ineffective attempts to find a world in our solar system that would resemble our Earth, information about Titan has given hope to the scientific community. This resemblance was revealed in 2005 when the automatic probe Huygens landed on the surface of the satellite. Over the course of 72 minutes, the spacecraft's onboard photo and video camera transmitted to Earth a photo of Titan's surface and other video material about this distant world. Although this cosmic body is a moon of Saturn, it has all the attributes of a full-fledged planet. Clouds, rain, rivers, lakes, and even an underground saltwater ocean. With its methane seas and thick atmosphere, Titan is in every way the most Earth-like world we've ever found. Generally speaking, the atmosphere is a cocoon of gas molecules that envelops the entire planet. The Earth's atmosphere protects us from harmful solar radiation and also contributes to redistribution of heat and the mixing of gases, which ultimately has a significant impact on the biosphere. Our solar system is home to over 180 moons, but Titan is unique in that it is the only moon with a dense atmosphere. The moons of the solar system also have atmospheres, but often they are so subtle that their existence can simply be overlooked. But Titan stands out from the rest. Its atmosphere is literally titanic. It is so dense and opaque that for centuries it's prevented scientists from assessing the true size of the satellite. In 1944, astronomer Gerard Kuiper discovered Titan's gaseous envelope using a powerful new telescope, but it's only with the sending of the probe Huygens the scientists managed to reveal the surface of the satellite, which has been so carefully hidden for more than 350 years. Titan's atmosphere is more similar to Earth's than to any other. It is mainly composed of nitrogen, about 95%. For comparison, the nitrogen content of the Earth's atmosphere is about 78%. The remaining 5% of the gaseous envelope of Saturn's moon is methane and other carbon compounds. At Titan's surface, atmospheric pressure is about 60% higher than on Earth, which is about the same pressure a person would feel swimming about 50 feet below the surface of an ocean on Earth. Because Titan is less massive than Earth, its gravity does not hold its gaseous shell as tightly together, so the atmosphere extends 10 times farther than ours, nearly 600 kilometers thick, or 370 miles. The composition of the atmospheric gas is as follows: about 95% nitrogen, 5% methane, and a small amount of ethane, acetylene compounds, propane, carbon dioxide, carbon monoxide, helium, and cyan. Note that each layer of the atmosphere has its own composition and concentration. High in Titan's atmosphere, methane and nitrogen molecules are separated by ultraviolet light from the sun and high-energy particles accelerated in Saturn's magnetic field. Part of these molecules recombine to form various organic chemicals, and often include other elements essential to life. Some of the compounds that form as a result of this separation and processing of methane and nitrogen create a kind of smog, a thick orange haze that makes the moon's surface difficult to see from space. The origin of Titan's atmosphere remains a mystery. Researchers defend a hypothesis that ammonia in the form of ice was delivered by comets and converted into nitrogen by collisions or photochemical processes. In another hypothesis, scientists focus on another common component of comets, which are simple organic compounds. In fact, the remaining 5% of Titan's atmosphere is almost entirely methane. It is constantly being removed from circulation, transformed into larger, heavier molecules, and deposited on the surface of the satellite. Therefore, the methane reserves, as the scientists suggested, must be constantly replenished. In order to confirm their hypothesis, the scientists reviewed the data obtained by the European probe Rosetta, which approached the famous comet Chury a few years ago. Comets are primitive bodies, formed at the beginning of the solar system, and many of them could even be part of larger bodies, planets, and satellites. Indeed, dense, organic-rich rocks can be found in their subsurface. Scientists have simulated such a scenario, showing that organic materials embedded in Titan in this way can be constantly decomposed under the influence of high temperature and pressure in its depths. This continuous process leads to the release of gas, mainly methane, which seeps to the surface. According to the author's calculations, such a hypothesis can explain about half of the total mass of nitrogen accumulated in the dense and mysterious atmosphere of the satellite. A characteristic feature of Titan's atmosphere is its anti-Earth effect. The presence of organic hydrocarbon molecules in the lower layers of the atmosphere neutralizes the greenhouse effect created by a huge concentration of methane. As a result, the surface of a celestial body cools uniformly due to the presence of hydrocarbons. The same processes in the gravitational field of Saturn determine the circulation of the atmosphere of Titan. Such a picture contributes to the formation of actic climatic processes in the atmosphere of Saturn's moon. It should be noted that Titan's atmosphere is constantly losing weight. This is due to the absence of a strong magnetic field in the celestial body, which is not able to contain the air-gas shell, which is under the constant influence of the solar wind and the gravitational forces of Saturn. To date, the atmospheric pressure on the satellite of the ring giant is 1.5 bar. This is invariably reflected in the weather conditions, which change with the concentration of gases in Titan's atmosphere. The creation of weather conditions on Titan is carried out mainly by dense clouds, which, unlike terrestrial air masses, are made up of organic compounds. These clouds are atmospheric formations, which are the source of precipitation on Saturn's largest satellite. Due to the low temperatures, the atmosphere of the celestial body is dry. In addition, the highest concentration of cloud cover was found in the polar regions. Due to the low temperatures, the humidity in the atmosphere is extremely low, so that the precipitation on Titan is methane ice crystals and frost, consisting of compounds of nitrogen, ethane, and ammonia. On the other hand, researchers believe that, just as on Earth, there's a global climate change on Titan. The Cassini spacecraft detected a stormy boom cloud in Titan's atmosphere in September 2010. To understand how this cloud could have formed on Titan's surface, researchers from the University of California modeled a global climate model of Titan's atmosphere in 3D. It turns out that Titan's climate is very similar to Earth's climate in the tropics and around the equator. The planetary waves that form storms on Titan's surface are very similar to the storms that occur in the tropical areas of our planet, although our storms are significantly less intense. Titan's surface is one of the most Earth-like places in the solar system. Although the temperatures are much lower and the surface itself has a different chemical composition, Titan's surface is an extremely curious object from a geological point of view. On Shangri-La, a huge plain near the equator of Titan, there are dunes that cover about 13% of Titan's surface and are easily confused with the dunes of Namibia. In this African country, the sand mountains can rise up to 300 meters high, or 980 feet, while on Titan, the dunes are a bit more modest, rising from 100 to 175 meters, or almost 570 feet. However, these dunes are not made of sand. They're made of black hydrocarbon grains and frozen pieces of methane and ethane. It all looks like coffee grounds. To explain the formation of these dunes, scientists have exploited meteorological data transmitted by the spacecraft Huygens, which shows that dust devils can contribute to the formation of the surface of Titan. Titan contains a lot of organic matter in suspension, which are formed by radicals that appear when nitrogen and methane decompose under the influence of sunlight, then settle as sand. Sand granules on Titan's surface vary in size from 5 to 200 micrometers. The weathering process of the rocks on the moon contributes significantly to their appearance. The Cassini Interplanetary Station has recorded several active dust storms in the equatorial regions of Titan. This means that the Moon has an interesting similarity with Mars, the presence of an active dust cycle and the possibility of the formation of dust devils, which lead to the formation of dunes. In a study, scientists from the University of Idaho tried to test whether such dust devils can actually exist in Titan's atmosphere. To do this, the researchers studied data obtained by the Huygens space probe, which landed for the first time on the surface of Titan in January 2005. By studying the parameters of pressure, temperature, and wind speed, the scientists discovered that such atmospheric phenomena play a key role in the formation of the so-called aeolian reliefs, in this case, the dunes. Titan's dust devils can be up to 500 meters or 16,040 feet in diameter, and the wind speed in the eye of the devil can be several meters per second. That's enough to lift the sand pellets. Scientists hope as early as 2034 they'll be able to confirm their findings with the Dragonfly space mission that's scheduled to land on Titan. In another context, under a thick cover of methane, the photographic lenses and cameras of the space probe Huygens have discovered entire continents, separated by numerous lakes and seas, another impressive similarity between the Earth's surface and that of Titan. However, these formations, some of which are as large as the Great Lakes of North America, are not made of water, but of methane. Moreover, it is the gas circulating on the surface of Titan that's the origin of the hills and valleys, similar to White Canyon in Utah. As on Earth, there are many rocky and mountainous formations on the continents. There are deep crevices and depressions. These are replaced by vast plains and valleys. On the other hand, the rocks scattered on the surface of Titan also look familiar. However, they're made of water ice that took this form in the incredibly cold environment of the Moon. Despite its cold and stony nature, the satellite is in an active phase and tectonic processes are observed. This is facilitated by tidal forces, which are caused by Saturn's giant gravity. Scientists also suspect the existence of volcanoes on Titan. However, instead of molten rock, they would spew liquid water. On the surface of Titan, one sometimes feels at home watching the clouds floating in the sky, which sometimes pours methane rain on the surface of the satellite. No other world in the solar system other than Earth has such liquid activity on its surface. The variety of landforms on Saturn's moon is astounding. Scientists have explained how soft organic dust turns into grains of sand and rock, and how winds and rains form dunes and carve canyons. Titan, Saturn's large moon, is the only known body in the solar system outside of Earth that has a seasonal fluid cycle. Scientists at Stanford University have shown how this fluid cycle, combined with the sediment cycle, can explain Titan's diverse landscape. From a distance, Titan looks like Earth. It's surrounded by dunes at the equator, plains dominate at mid-latitudes, and lakes and canyons are found at the poles. Thanks to the cocoon of the dense atmosphere, it rains and the wind blows, but instead of water, liquid methane flows on Titan, and the nitrogen wind collects the hydrocarbon sand dunes. The mechanical properties of this sand are very different from the properties of the usual silicate sedimentary rock that covers the Earth. The main difference is that hydrocarbon particles are much less durable and must be quickly reduced to dust, while relatively large granules are required to form dunes. The question is, how do these simpler organic compounds maintain their size? On Earth, under the influence of erosion, stones and silicate minerals eventually break down into small particles. Wind and water currents carry these particles to sedimentation sites where pressure, groundwater, and sometimes heat cause the particles to fuse back together to become rocks. Scientists suggest that a similar cycle should exist on Titan. It's obvious that there too, the forces of nature grind the rocks into sand and dust. However, it's not known how the dust turns back into rocks and sand for the dunes. Ooids, spherical millimeter-sized grains often found in the shallow waters of tropical seas, have helped answer this question. These grains have the particularity of being formed by chemical precipitation. Calcium carbonate from water is deposited in layers on grains of ordinary sand. The particles rub against each other and decompose, so the calcium carbonate returns to the water and is deposited again. The process of deconstruction and formation offset each other, and the particles retain their size. The researchers suggested that in the same way on Titan, dust particles merge with each other, forming grains of sand and rocks which are then crushed by the wind. Taking this hypothesis into consideration, the team of scientists modeled the sedimentary migration cycle using climate and atmospheric data collected by the Cassini mission. It turned out that the process of melting, the pattern of winds and precipitation, explained the diversity of landscapes. The strongest winds blow in the equatorial belt, so that the sedimentary rocks are constantly destroyed and form dunes. In the middle latitudes, the wind is much weaker, but the humidity is higher and the particles melt into dense rocks and form the plains. At the poles, rains and rivers dig deep canyons and labyrinths in the rocks, a landscape similar to the karst on Earth. Cassini's instruments have captured huge cloud systems and darkening on Titan's surface. The best explanation for this is the moisture that's rained and flooded large areas. Of course, in this case, we're not talking about water, but liquid methane. Observations from the Cassini probe have shown that as the hours of sunlight increase, the circulation of atmospheric masses also changes, generating powerful clouds over the equatorial regions of the satellite. They're saturated with methane, which plays the same role in Titan's very cold atmosphere as water does in Earth's atmosphere. Over time, the clouds spread rain that fills the lakes with liquid hydrocarbons. Cassini also discovered similar lakes in the subpolar regions of Saturn's moon during a radar survey, but recent observations have provided strong evidence that seasonal or permanent reservoirs of liquid substances may exist in Titan's equatorial regions. Titan's equator was previously thought to have a very dry climate. Apparently, Titan's climate is similar to the Earth's tropics. As you know, in the tropical regions of Earth, receiving a lot of sunlight, a zone of updrafts is created, and clouds are formed that encircle the planet. On Titan, this is the case in the equatorial regions during the change of seasons. In summer and winter, when precipitation falls in the polar regions of the satellite, droughts set in at the equator. Isn't it amazing to see such familiar activity as heavy rainfalls, storms, and seasonal weather changes on a distant, cold satellite? Titan's resemblance to our living planet is confirmed by the presence of a liquid structure. On Saturn's largest moon, Titan, lakes and seas of liquid hydrocarbons have been discovered. During its latest approach to Titan, the Cassini spacecraft provided an unprecedented view of these methane lakes. In a paper published in the journal Nature Astronomy, researchers report that some of these lakes are more than 100 meters deep, that's almost 330 feet deep, and have been fed by methane fallout for thousands of years. Others are only a few millimeters deep and exist for only one season. Outside of Earth, Titan is the only object in the solar system with clear evidence of stable liquid on its surface, but this liquid is not water, but hydrocarbons like methane. Because of the low temperatures, which average negative 180 degrees Celsius or negative 292 degrees Fahrenheit during the day, these hydrocarbons are stable on the surface. However, despite the obvious differences, there are surprising similarities between Titan and Earth. Like the water cycle on Earth, Titan also has a complete methane hydrological cycle, linking the atmosphere, surface, and interior of the satellite. Researchers suggest that Titan's lakes have existed for millennia and were created by methane rains that dissolved surface rocks. The experts also note that the reservoirs are increasing in volume due to the influx of hydrocarbons as a result of precipitation, the amount of which exceeds their flow through the ground. In another study, scientists report the discovery of ghost lakes, which are shallow pools that have evaporated or drained into the ground during Titan's transition from winter to spring. The researchers also note that some of Titan's lakes are at high elevations. The data show that these lakes, like others in the North Polar region far from the major seas, have a liquid surface height of several hundred meters above sea level, so they likely feed on local sediments. In addition, on Titan, rivers have been discovered with springs, winding channels, and deltas, places where streams flow into marine basins. According to data from the images, some of Titan's rivers have channel lengths of more than 1,000 kilometers. Almost all of Titan's liquid mass is concentrated in marine basins and lakes, which occupy an impressive area, as much as 30 to 40% of the total surface of the celestial body. The evidence of large accumulations of liquid medium on the surface of the satellite was a huge discovery, which has long baffled astronomers. Subsequently, it was proven that the bright region of Titan is a huge pool of light hydrocarbons and liquid nitrogen, called the Kraken Sea. By area, this imaginary reservoir is larger than the largest salty inland sea on Earth, the Caspian Sea. Another object of no less interest is the Lygian Sea, which is the largest natural reservoir of liquid methane and ethane. In addition, a new analysis of data from the probe Cassini showed that the depth of the central part of the Kraken Sea can reach 300 meters, or 980 feet. In 2014, the probe took measurements in 3 areas of the Kraken Sea. For example, radar observations showed that in the Murray Gulf area, an estuary in the northern part of the sea, the depth reaches 85 meters, or 280 feet. However, in the central part of the Kraken Sea, it was not possible to reach the bottom. Either it is too deep, or the composition of the liquid is different there, because it absorbs too many radio waves, not allowing us to pick up the signal reflected from below. The second hypothesis is unlikely because the liquid in the sea is constantly mixed. Calculations show that in this case, the depth of the central regions of the Kraken Sea is at least 100 meters, or 330 feet, and in some areas it can reach up to 300 meters, 980 feet. In general, the work of Cassini has provided accurate information on the composition of the liquid environment of Titan's seas and lakes. Using data from photographs and computer simulations, the composition of the liquid on Titan has been determined to be 76 to 80% ethane, 6 to 7% propane, while methane represents 5 to 10%. In addition to the main elements presented as frozen gases, hydrogen cyanide, butane, butene, and acetylene are present in the liquid. The main accumulation of water on Titan is somewhat different in nature from the Earth form. Huge deposits of superheated ice, consisting of water and ammonia, have been discovered on the surface of the satellite. It's assumed that below the surface, there may be large natural reservoirs filled with liquid water containing dissolved ammonia. Under this aspect, the internal structure of the satellite is also interesting. All these discoveries underline the existence of a very dynamic fluid cycle on Titan. Like the Earth's water cycle, the hydrological system of Saturn's moon has seasonal variations. In addition, the scientists mentioned the potential habitability of these lakes, highlighting the location, size, and longevity of these surface fluid reservoirs. The possibility of life on Titan has long been discussed by scientists. Many researchers thought it was impossible because Titan's so far from the sun, and because of that, it's too cold. In addition, the atmosphere of the satellite, in addition to nitrogen, is also rich in toxic methane, and there's no water at all on Titan. This is why it was previously considered an unlikely place for the origin of life. However, the latest study by a team of scientists led by David Shalloway of the American Cornell University shows that life on Titan could have formed in the absence of liquid water. The scientists studied the chemical composition of Saturn's moon and concluded the hydrocyanic acid on Titan could create conditions for life to emerge. We know that hydrocyanic acid is toxic to humans. Indeed, this substance is found, for example, in tobacco smoke and is released during the decomposition of polyurethane. However, even in our body, hydrocyanic acid can perform useful functions. For example, it's produced by neurons to help improve the efficiency of nerve impulse transmission, and it is secreted by leukocytes and contributes to the death of harmful microorganisms. As a result of chemical reactions occurring on Titan, hydrocyanic acid molecules contribute to the formation of polymers, in particular polyamides. These organic compounds are capable of absorbing a wide range of light rays, so that it's possible to absorb even the small amount of sunlight that penetrates Titan's atmosphere. In addition, polyamides can become the basis for the formation of amino acids and nucleic acids, the basis of proteins and DNA. Polyamides can exist in a variety of structures and perform many functions, even at low temperatures, and especially under Titan conditions. For example, polyamides like bricks serve as a catalyst base for the passage of primary chemical reactions. It's also been found that polyamides absorb light where Titan's atmosphere is more transparent. This light can be used as an energy source for the reactions. The researchers used and analyzed data obtained during the Cassini-Huygens missions. The results of the analysis of the samples collected by the spacecraft allowed the scientists to conduct computer simulations of the processes, during which it turned out that polyamide could indeed serve as a starting point on the path to the origin of life. Scientists know that hydrocyanic acid, the predecessor of polyamide, could play an important role in the processes of origin of life on our planet. Therefore, organic molecules, liquid lakes and seas filled with methane, and some amount of solar energy reaching the surface all suggest the possibility of an environment where some sort of exotic life form can form. But the researchers stress that their findings are purely theoretical and that no direct evidence has been found on Titan's surface. Thus, that life might not exist on this satellite of Saturn, even in an exotic form, not similar to the terrestrial form. In another context, throughout the study of Titan, scientists have not only discovered a large number of seas and lakes containing liquid carbonates, but have also discovered prebiotic chemical compounds that could, under favorable conditions, give rise to life on Titan. However, some scientists argue that the absence of oxygen in Titan's atmosphere is a strong indication that there's no life on this moon. Certainly, the presence of oxygen in the Earth's atmosphere is a clear difference between the atmosphere of Titan and our world, but it was not always so. In fact, about 3.8 to 2.5 billion years ago, there was no oxygen on our planet. Then microbes ruled the Earth. The air was filled with methane produced by these simple microorganisms, and they thrived quietly in the oceans. There are suggestions that sometimes Earth's methane atmosphere could form the same orange haze that exists on Titan today. In fact, such an atmosphere could help the development of life on our planet by maintaining a roughly constant temperature on Earth and by reflecting most of the sun's ultraviolet radiation, which has a harmful effect on DNA. On the other hand, nitrogen and methane are two chemical elements in the atmosphere of Saturn's moon that can create a wide variety of organic molecules. Indeed, under the influence of solar radiation, these elements can be split into individual atoms, hydrogen, nitrogen, and carbon, which can then be assembled into a variety of complex compounds that are deposited on Titan's surface. These compounds are called organic because they contain carbon, the main building block for the formation of life on Earth. Researchers want to know the nature of these compounds on Titan. Are they similar to those that contributed to the emergence of life on Earth? Whether microbial life exists on Titan is perhaps the most intriguing question for scientists. For one thing, a very important component for life is missing from the surface of the satellite: liquid water. In this context, scientists believe that liquid methane can take over the functions of liquid water on Titan. It's quite suitable for some exotic life forms. After all, we know that organisms on Earth can live in absolutely incredible conditions: extreme temperatures, high radiation, and no water. Can creatures like this survive Titan's hostile environment? This life could take the form of microbes and extremophiles in the inner ocean, or could take the even more extreme form of methanogenic life forms. As has been suggested, life could exist in Titan's liquid methane lakes, just as organisms on Earth live in water. Such organisms would inhale dihydrogen H2 instead of oxygen gas O2, metabolize it with acetylene instead of glucose, then exhale methane instead of carbon dioxide. Moreover, in order to reveal what led to the emergence of life on Earth, scientists are conducting experiments with simulated environmental conditions of the ancient Earth in laboratories. Again and again, they try to find the catalyst for the reaction that transformed the primordial soup of organic matter into the exceptional biodiversity that exists today. But the length of time that life has existed on Earth does not give laboratory experiments a chance. This is where Titan comes in. Many scientists believe that this satellite could become our virtual laboratory of prebiotic chemistry that's existed for a long time. It only remains for the space probe Dragonfly, which will fly to Titan in 5 years, to discover the results of these experiments in different geological regions of the satellite. Note that Dragonfly will land in the Celt crater, where an abundance of organic compounds could mix with liquid fluids on the surface for long periods of time, creating conditions that could support life. Is Titan a world similar to the Earth of billions of years ago? Scientists have every reason to think so. Using the Dragonfly experiment, they'll try to discover how similar the chemical reactions in the atmosphere of the two worlds are. It is true that at great distances from the sun and in the freezing cold, water on Titan is preserved exclusively in the form of ice, and light hydrocarbons, mainly methane, play the role of liquid. However, simulations have shown that the impact that created the largest crater on Titan could have created a warm lake filled with water and organic matter. Specifically, liquid water may be present deeper beneath Titan's icy crust, which is estimated to be hundreds of kilometers thick. This is a unique world, and its dynamics, theoretically, even allow the existence of local life, albeit very different from our own. Scientists at the Lunar and Planetary Science Conference showed that water from deep within Titan should at least sometimes mix with hydrocarbons on the surface, creating a favorable biochemical environment. This happens because of cracks that appear in the satellite's crust due to collisions with comets and asteroids. The researchers simulated a collision that would have resulted in the largest impact crater on Titan. Minerva, which measures about 425 kilometers in diameter, or almost 265 miles, and is estimated to be about 1 billion years old. Calculations showed that it could be due to the fall of a celestial body with a diameter of 34 kilometers, or 20 miles, and a speed of about 7 kilometers per second, or 4 miles per second. The energy of the impact was enough to bring to the surface not only water, but also a lake of liquid water, which froze for 1 million years. According to scientists, this may well be enough for the birth of the first primitive organisms and the launching of powerful mechanisms of biological evolution. Minerva is perhaps not the only one in this case. The appearance of other large craters could be accompanied by the same heating and mixing of water and organic matter. NASA's future Dragonfly mission, which should start in 2027 and arrive on Titan in 2034, will finally confirm this. Scientists have already identified some possible markers of prebiotic chemistry, such as organic compounds and molecules that resemble those thought to have existed on the early Earth. So the Dragonfly ship will explore whether conditions are suitable for life by studying the global methane cycle, how the atmosphere interacts with surface materials, and where water may mix with organic matter. While Mars is definitely scientifically interesting, not all scientists find it attractive as a long-term human habit. However, outside of the red planet, Titan represents the best place in our solar system where conditions for a long-term, self-sustaining human settlement can be described as suitable. When scientists talk about the possibility of life outside of Earth, as a rule, their attention is given to planets and satellites, which have at least 3 conditions for the potential formation of living organisms, namely warmth, a habitable atmosphere, and water. To begin, let's be clear that Titan is a moon that is more like a planet in many ways. This giant moon is the only moon in the solar system with a dense atmosphere that's about 1.5 times the surface pressure of Earth's atmosphere. None of the 184 other moons in the solar system has such an atmosphere. Like Earth, Titan's atmosphere is composed primarily of nitrogen. In our planet's atmosphere, nitrogen's over 78%. Titan is also the only place in the solar system, except for Earth of course, where it rains and where fog forms. Titan's dense atmosphere is useful because it means you don't have to wear a bulky spacesuit when you're on Titan. But the main reason's simple: Titan's atmosphere will help us survive. In space, radiation is deadly. Energy particles from the sun, and especially galactic cosmic rays, penetrate human tissue, causing cancer and cognitive impairment. To stay within NASA's current cancer risk limits, astronauts can travel beyond low Earth orbit for up to 200 days. A trip to Mars is expected to take over 600 days. But these destructive particles cannot reach the surface of Titan. They are absorbed by the atmosphere, which means it's a safe environment for humans. The atmosphere of Mars is not dense enough to provide reliable protection from galactic cosmic rays. People living on Titan can walk, or rather bounce since the gravity is 14% of Earth's gravity, a little less than on the Moon, of course in a suit to keep warm. Titan is cold. The surface temperature is around negative 180 degrees Celsius, or negative 292 degrees Fahrenheit, and people will have to wear respirators to breathe oxygen because the atmosphere is mainly composed of nitrogen. The light on Titan is a bit dim, like just after sunset here on Earth, because of the haze particles of the dense atmosphere. People living in a hemisphere of Titan still facing Saturn will have a great view of the ringed planet. Furthermore, it's the only place in the solar system other than Earth where the familiar fluid cycle is known to exist. Clouds fall to the surface of the moon and fill the lakes and seas, then evaporate and vanish into the sky. Titan is also thought to have an ocean under the ice, similar in salinity to the Dead Sea. Because it's so cold on Titan, all the water is frozen, and the lakes and seas are made up of liquid methane and ethane. These hydrocarbons, like natural gas here on Earth, are abundant on Titan, not only in the lakes and seas, but also on the surface and in the atmosphere. Saturn's largest moon, Titan, is a truly unique place. a more interesting destination than the standard option of Mars or the Moon, despite the fact that Titan only receives about 1% of all the sunlight that the Earth receives, and that the highest temperature on the surface of the satellite only reaches negative 180 degrees Celsius, or negative 292 degrees Fahrenheit. So, for the first time in the history of the study of extraterrestrial space outside of Earth, a celestial body has been discovered with conditions that resemble those that prevailed on planet Earth in the early years of its existence. All this suggests that we are dealing with a celestial body which could be another oasis of life in our solar system. Studies of the composition of the atmosphere and liquid medium of Saturn's satellite have revealed the presence of useful substances necessary for the life of organisms. It's assumed that under certain conditions during the study of Titan, living organisms can be found on this moon. In this respect, further study of Saturn's largest satellite becomes relevant. However, if Titan is so good and interesting, then why has it not yet been mastered? Why are most missions directed to Mars and the Moon? The problem is the distance. The flight time to Saturn can vary, from 4 years to almost 7 years, depending on the orbital relationship with Earth at launch. Without significant energy advances, this would mean an extremely long trip to and from any potential colony. In addition, there are many obstacles to overcome, not the least of which is studying how humans will live and work in microgravity. Growing food on Titan using crops, as we do here on Earth, will not be efficient given the low flux of solar energy reaching Titan's surface and the already low efficiency of photosynthesis here on Earth. Titan's inhabitants will need biotechnology and non-traditional products. Perhaps future humans on Titan will be able to use some sort of artificial photosynthesis. All that remains is to wait for a scientific breakthrough. Through the studies conducted over the past decade, humanity is dealing with a unique object in the solar system. It turned out that Titan is the only celestial body, besides the Earth, which is characterized by all three types of activity. On Saturn's satellite, there are traces of constant geological activity, which are the confirmation of its living tectonic activity. The nature of Titan's surface is also interesting. Its structure, composition, and landscapes speak in favor of the fact that the surface of Saturn's moon is in constant motion. Here, as on Earth, under the influence of winds and precipitation, we observe soil erosion, rocks are altered, and sediments are deposited. Moreover, the composition of the satellite's atmosphere and the circulation processes that occur there have shaped Titan's climate. The discovery of a huge ocean of liquid water, 55 to 80 kilometers, about 110 miles, beneath the icy floor, adds Titan to the handful of worlds in our solar system that could potentially host a habitable environment. In addition, Titan's rivers, lakes, and seas of liquid methane and ethane could serve as habitats on the moon's surface, although any life there would likely be very different from life on Earth. All of these signs speak in favor of the fact that life can exist on Titan under certain conditions. Naturally, it will be a different form of life than terrestrial organisms, but its very existence will be a colossal discovery for humanity. In the summer of 2019, NASA announced that the next target in the solar system was the unique and richly organic world of Titan. Advancing the search for the building blocks of life, the Dragonfly mission will make multiple excursions to explore sites around Saturn's icy moon. Titan is one of the most Earth-like worlds, the moon that may shed light on the history of our home planet and identify processes that likely shaped the development of life. Although there's no evidence of life on Titan yet, its complex chemistry and unique environment have made it a destination for new research, such as providing clues as to how life might have arisen on our planet and searching for chemical evidence of past or present life.